So yeah, I'm going to talk about some work on motion groupoids, which, among other places, is available at this archive number if anyone wants to read more about it. It's work together with Paul Martin and Joao Faria Martins. I didn't get pictures of them. Everyone else seems to have pictures of all their collaborators, so you'll have to just look for them in the audience. Okay, so I'm going to start with a brief overview of everything that I'm planning to say. So the first thing I'm going to talk about, so this is going to be the vast majority of the talk. This is going to be the thing we're going to do in the most detail. So for any pair consisting of a manifold M and a submanifold, for example, the boundary, so this would be some fixed submanifold, we can construct the motion groupoid. So roughly, this is a groupoid where objects are subsets of the manifold. So maybe points in a two-dimensional manifold, maybe loops or knots in a three-dimensional manifold, but really our construction is very flexible. And roughly morphisms are equivalence classes of continuous flows of the ambient space which act on our chosen subsets. And looking at this, we recover the classical definition of the motion group associated to a manifold and a submanifold pair, and we do that by looking at the morphism group in this category at the object M. And in this way, we can obtain groups isomorphic to the familiar braid groups and perhaps familiar to some loop braid groups. And the next thing we're going to do is look at the construction of a different but related groupoid, which also takes as input this same pair of a manifold and a submanifold, and this is called the mapping class groupoid. So here, morphisms are now equivalence classes of homeomorphisms of M, rather than these continuous flows. And the object set is the same. And again, we can get groups isomorphic to the braid groups and the loop braid groups. So then, of course, the obvious question is, well, in general, what's the difference between these two things? So that's the last thing we're going to talk about. How to construct a functor between these two groupoids and when this functor becomes an isomorphism. So in particular, this functor becomes an isomorphism if the pi0 and pi1 of the appropriate space of homeomorphisms of the manifold M fixing this subset A is trivial. So for example, if we take the unit interval, unit square, unit box, anything like that, and fix the boundary, we get an isomorphism. So in particular, that explains the braid, loop braid cases appearing in both settings.
Sorry, can you say it again? What is a PM?
So this is the power set. So this is all subsets of M. So this is what I'm saying, that's really very flexible, but really this is just a brief overview, and we're going to go into everything in more detail.
When you say X is fixed by the flow, do you mean at time one it's back where it started, or it's fixed at every point in time?
You said X, and I can't see an X.
Sorry.
A?
Sorry.
Yeah, okay, just because it depends whether you're asking about N or A. A is completely fixed, point-wise fixed for the entire flow. Okay, good, so that's a brief overview of what we're going to talk about. So now let's talk a little bit about the motivation. So I'm sure it's going to come as no surprise to anyone here that we were interested in modeling particle motion in topological phases. But it's perhaps worth spending a little bit of time talking about what, in particular, new our construction does over what existed before. So we use this groupoid framework. So one thing we do, we have these very general, this very general setup where we can pick any ambient space, we can pick any subset, so we can think of any particle type here. Putting it into this categorical setting, organizing everything in a groupoid, allows us to study objects in a unified way, so we can start asking questions about skeletons. So when we just look at the group, we can look at group isomorphism, but we could have isomorphic groups that are connected in the groupoid and also isomorphic groups that are not connected in the group. We can make use of higher categorical structures, for example, monoidal structures, to help us understand presentations of various things in these groupoids. Also, putting everything in this categorical setting connects to the TQFT picture where we're thinking of particle motion as maybe generalized tangles or defect TQFTs, these embedded things. So that's all easier to see once we've already put this in the groupoid setting. And also the groupoid allows for morphisms which do not start and end in the same configuration. And this is potentially useful for constructing presentations. And then, yeah, I think I have one more. So also we know that in many cases motion groups give interesting algebraic structures that have been very well studied, led to lots of interesting mathematics. So we fully expect this to be replicated in new settings here. So obviously this is very quick and many of these points won't necessarily make sense without the full picture of what these things are. So if at the end of the talk there's any of these which isn't clear why these are true, please do ask. Okay, so let's get started on what the motion groupoid looks like. So first I'm going to need to introduce some notation. So I'm using this bold-faced top to mean the category of topological spaces and continuous maps between them, which of course means that if I write top xx, this is the set of all continuous maps from x to x, then I'm just going to decorate this with this superscript h to mean I'm restricting to homeomorphisms, which then is a group. And then I'm going to capitalize this to mean I'm thinking of this set as a space where I've given it the compact open topology. So I guess not everyone is familiar with what the compact open topology is. I'm not explicitly going to go through the definition of this, but I'm just going to write this lemma, which I think gives some kind of intuitive idea. So whenever Y, the space that we're mapping into, is a metric space with metric D, then we can define a metric on the space of, on the set of maps top x, y, by saying that the distance between a map F and a map G, D prime, the distance between F and G, is given by looking at the least upper bound of the distance between the image of every f of x, every pair f of x, g of x. And this is the same as the compact open topology whenever Y is a metric space. Okay. And then we're also going to need versions where we fix this set A pointwise. So we only consider the subset of maps where A is completely fixed. Okay, so now we're going to fix some choice of a pair consisting of a manifold M and a submanifold A. We say that a flow in M is a map F. So here I'm using this bold-face I to just mean the unit interval, so I don't have to write 0, 1 everywhere. So bold-face I always just means the unit interval. So this is just a path in the space of homeomorphisms of M, which fixes the subset A. And then we add the condition that these paths must start at the identity homeomorphism. And then I'm just giving this notation for this set flow M. Okay, so some examples. If we pick any manifold M, we have a flow which just at all t is the identity homeomorphism. And I'm going to use that one quite a lot, so I'll give it some notation, which is just this capital identity means the identity flow. What's another example? We could think of the unit circle. And then we can parameterize this as usual with an angle between 0 and 2 pi. And then we can consider functions which, so we have a homeomorphism for every phi which rotates the circle by phi. And then we can think of a flow which gradually rotates the circle by pi. Okay, and then here's a example pictorially. So this is the disk. This is a flow which fixes the boundary of the disk. So we're representing sequential points of this flow. We're gradually rotating the interior of the disk, but leaving the boundary fixed. Okay. And so given a flow, there's several ways we can obtain a new flow. So if we have a flow F, we can do this pointwise inverse. So we can define f to the minus 1 at t is just given by taking f of t to the minus 1. This is also a flow. And a point to note, this uses that this space, top HMM, is a topological group. So because we chose that M was a manifold, this is true. But all the theory that I'm going to talk about works also if M is any locally compact, locally connected space. So what this means to be a topological group is that the product map and the inverse map is continuous. So in particular, what we're using here is that the inverse map is continuous. And then we also have another way we could obtain something that looks a little bit like an inverse that I'm going to call bar. So if we have a flow F, we can take F bar, so this is more like the inverse in the usual fundamental groupoid. So we take the path and then we do 1 minus t, we reverse the direction along the path. But we also had the condition that our flows had to start at the identity. So to get a flow, we have to add in this f1 to the minus 1 here. And similarly, we have a couple of different compositions we could do. So first, if we take a pair of flows, we have the star composition. Oh, no, gone too far forward. We have the star composition, so we take a pair of flows, F and G, and we can construct this flow G star F. And this looks like the composition in the usual fundamental groupoid as well. We do F twice as fast. Then afterwards, we do G twice as fast, but we compose it with this F1 to ensure that the endpoint of F matches up with the start of the second segment. And so the star composition is this composition that looks more like this real-life picture that we're trying to model, where we do one flow, we move particles in some chosen way, and then we follow this by doing the next one. But of course, this composition at this point is not associative, not unital, so at the moment we just have that this forms a magma. Okay, and then we have this other composition called the dot composition, which is like the pointwise inverse. So we take a pair of flows and we define this flow G dot F, where G dot F at any t is defined to just be G of t composed with F of t. And so this is less like the real world picture, but is going to be useful in various proofs to give results about these things.
Question: are these two products the same? Is the same in certain cases, or they're never the same?
I am sure that there are certain cases where they're the same. If you take the identity, in general they're not. But I'm sure you can construct some other examples where they're the same.
Okay, I'm just asking this since. I mean, a flow, it seems like it is a path starting from a certain point, a fixed point in the space of self-homeomorphisms, and that space. I mean, at least if it's a topological group, I'm thinking like the operations, the product operations in pi 1 of those. You can define it either as as your first way, like a concatenation of path, or you can use the product operation in the topological group. These two operations, they actually define the same product if the group is a topological group. Well, when I say the same, I guess you need to define equivalence class on path, but here you haven't introduced this equivalence class.
Okay, so
exactly that two things are.
Okay, so if you define the equivalence class, okay,
Sorry.
yeah. That's
yeah,
good.
so I guess you answered your own question halfway through your question. Yeah, we haven't gone to equivalence yet, and I think it's worth taking time and doing this slowly, because of course all of these equivalence relations are not things that necessarily exist in the real picture we're trying to model, and these are all mathematical choices to come up with a mathematical structure that we can work with. So I think it's worth going carefully over this and kind of highlighting where we're making these choices. But yes, in the end, we will come up with a motion groupoid where either of these products can be used. That is definitely where we're going. And just to highlight again that this uses that we have a topological group, so in various generalizations, you might construct, this is something to be aware of that might not hold anymore. Okay, and then in this case, we already have straight away that these flows with the dot composition becomes a group with the identity and this dot composition, the identity flow. And lemma, these things are path equivalent. And so this can be proved by explicitly constructing appropriate homotopies. Okay, so then what do we mean by a motion? So to construct a motion, we take one of these flows, F, and then we also choose some subset, N, which lives inside our ambient manifold M, and we just look at where F sends N. So we have this triple consisting of a flow, a subset, and the image of a flow at the end, the image of this subset at the end of our flow. And we might sometimes use this notation where we draw this a little bit like a map, but we use this curly arrow because F isn't really a map from N to N prime. Okay, and then we also introduce this notation, M, for just the set of all motions from N to N prime. And then we could represent this pictorially. So here, our light gray space is the space of homeomorphisms top HMM. Our motions are these paths, which must start at the identity and live inside top HMM. And okay, I haven't explained to you what homeo M prime is, but this darker gray patch is homeomorphisms from N to N prime. So this red path B becomes a motion from N to N prime, and this blue path becomes a motion from N to N. Okay. We can also observe that for any N, this identity flow always becomes a motion when paired with any N, becomes a motion from N to N. Also, if we take any F or G and we do the dot composition, this gives us a motion which behaves nicely. So we take a motion F from N to N prime, from N prime to N prime prime, and this gives us a motion from N to N prime prime. And so what we have is that we can construct an action groupoid dot, where the objects are this power set of all subsets of M, the morphisms are these motions, dot composition, identity, and this pointwise inverse. Similarly, we have that G star F becomes a motion in the same way. And so we can do a similar thing to obtain this algebraic structure with objects PM, morphisms, motions, and star composition, but we don't yet have a groupoid in this case. Okay, so as a little bit of an aside, there's other interpretations, there's other equivalent ways we could have defined what motions are. So if we similarly pick the same pair we had of MA and subsets, then I'm going to define this M superscript hom from N to M prime to be the subset of homeomorphisms M cross I to M cross I, which fix A cross I, such that we have that when at t equals 0, it just sends M to M0 to M0. For any t, it preserves M, and at the end, when t is 1, it sends N to N. And so it turns out that, as you might expect, there really is a bijection. The motions, as we define them, are exactly the same as these homeomorphisms M cross I to M cross I. And so what does it look like to prove that? So the key theorem you need is that there is a product homojunction for these things we're looking at, precisely because M is a manifold. And so this gives that the image is continuous, and then you also need to use that it's a topological group. to get that this really gives a homeomorphism m cross I to m cross I. And so what that tells us is that we really can think of motions as these pictures that we're used to, where we consider our ambient space cross I. So here's a motion of the unit interval I. So it's a map from I cross I into I cross I, where I've just added, at the moment it's considering the empty subset, I've just added these lines to show what's happening. And then we could put in some subsets. So here I'm considering n to be some interval. So on the left we have a motion n to n prime, and on the right a motion from n to n. And similarly, if I'd drawn some 3D diagrams instead of all 2D diagrams, we could have had the braid pictures that everyone's used to drawing and seeing. And then we could also have something like this, whereas this is just our motion rotating the circle, where I've put the cross I going inwards, and so as t progresses we move forward to that way through concentric circles, and we're just rotating this S1. And then in this picture, now our star composition just looks like stacking copies of I on top of each other. Okay, so now we have this very wild algebraic structure. In the end, we would like to end up with something that is a groupoid, because that's what we know how to work with, that's what we know how to study. So we're going to take a quotient. And the quotient we're going to do is in terms of what we call set stationary motions. So a motion f from n to n in M is called n stationary if for all t the path fixes n. And this is now as a set. So when we talked about the subset A, that always had to be fixed pointwise, whereas now we're just fixing n as a set. And then we just introduce this notation, set stat m superscript n, for the set of all motions, which are n stationary. And so, for example, if we let our m be the disk, and then we consider a flow which is gradually rotating the disk by 2 pi. Now if we let n be any circle centered on the center of the disk, then at all points this rotation preserves n as a set. We can also observe that if we again take m to be a disk, then n to be a finite set of points, then a motion f from n to n is n stationary if and only if it's precisely the identity pointwise on these points for all t. And more generally, this is true if we take n to be any totally disconnected subspace of M. So for example, we could take Q in R, and we would find that n stationary was essentially only the identity motions that we were quotienting by. Okay, so then what precisely is our equivalence relation? So we define motions f and g from n to n prime to be equivalent if g bar star f is in the path equivalence class of a set stationary motion. And this really is an equivalence relation that we refer to as motion equivalence. So what does it look like to prove that this really becomes an equivalence relation? Well, the way we do it is to quotient first by path homotopy. And then we find that the classes, the path classes, which intersect this set stationary, these set stationary sets, form a totally disconnected normal subgroupoid. And in general, it's always true that this g to the minus 1 star g1, g2 to the minus 1 star g1 condition always gives a congruence when you're looking at a normal subgroupoid, a totally disconnected normal subgroupoid. So what we've essentially said here is that we really do get a groupoid in this way. So we have a groupoid, see my pointer anymore, with objects this power set, motions up to this motion equivalence, star composition, this identity, and this f bar as our inverse map. Then we also would like that this really is the same as the groupoid, which we could have constructed by taking instead this dot composition and this pointwise inverse. And this turns out to be true. So how do we prove this? So it's sufficient here to observe that motions which are path equivalent really are motion equivalent. And so how do we prove that? So if G and F are flows which are path equivalent, then G bar, if we look at G bar star F, this is path equivalent to G to the minus 1 dot F using the proposition we had before that said that the star composition is path equivalent to the dot composition and the bar is path equivalent to the inverse. And then this is path equivalent to G to the minus 1 dot G using the assumption that P and G are path equivalent. And so then we have that G, yeah, that's what I just said, using that we already said they're path equivalent. So then we have that for all T and I, we know that G to the minus 1 dot G, which is just the identity on N, is equal to N. And so we have that this G bar star F really is a stationary motion. Okay, so what examples can we look at? So suppose N is some compact subset of the unit interval. So what does it mean to be a compact subset of the unit interval? It's essentially a union of points and closed intervals. And so we could assign a word to any such N by representing a point by A and an interval by B. And then we can order this word using the natural ordering on the unit interval. And if we look at another N prime, and then look at the word defined using this N prime, then there is a motion between N and N prime precisely if the word we assign to N and N prime is the same. And there is precisely one of them in the motion groupoid. Otherwise, it's empty. So this might make you think that the motion groupoid of the unit interval is always kind of boring. But what we find is if we instead consider, for example, I intersect Q, then we already get an uncountably infinite number of motions. So this really can become very wild, and this sort of hints at lots of fun lots of fun motion groupoids you could look at from here. So you could think of a hop flink in three-dimensional space, for example, and then you could ask the question of what happens if I put one puncture in one link of my hop flink. And then you could think, what happens if I put lots of punctures in one link of my hop flink? So what if I think of one link as being equivalent to taking only the rational points in one link of my hop flink and ask what the motion groupoid looks like in that setting?
But here, your second example, N is not compact, right? So maybe is that why is
And it's not compact,
that's
yes.
the why. Well, that's why the motion group could be contain more than one element.
Yeah. So the point is that I could have made the first example slightly more general by adding some open closed intervals and things. So that's true. Yeah. Okay, and then theorem we prove is that what we've constructed, if we take M to be D squared, and then take a finite subset, so a set of points in the interior of D2, we really do get something isomorphic to the Artin braid group. And that isomorphism is realized by sending a motion which moves points along the paths shown in this diagram to the elementary braid in the braid group. And also, if we take, a ball, if we take D3 with the boundary fixed, and we consider our subset L to be the unlink in the interior of D3, so N loops that are not knotted or linked, then what we get, Mott D3LL, is really isomorphic to what's called the extended loop braid group in this paper of Damiani. Okay, and then we have several nice lemmas about how we can relate different motion groupoids to each other. So potentially we can find out something about what one motion groupoid looks like and learn something about a different one from it. So if we take MA, a pair, and then a pair M prime, A prime, such that we have a homeomorphism from M to M prime, which sends A to A prime, then we always get an isomorphism of the motion groupoids, which on objects just sends every n to the image of this psi. And then for a motion, we just conjugate with the psi at every point. We also have that if we fix any pair MA, then we get an involutive endofunctor on the motion groupoid by taking the complement of the object. So it's fairly straightforward to see that a homeomorphism that sends n to m prime will also send m complement n to m complement n prime. And it's also interesting to notice that generally what we've done here is construct an isomorphism between things that are explicitly not connected inside the motion groupoid, unless n is homeomorphic to n complement n. Okay. So then something we do in the paper is we prove several theorems about different ways we could have constructed the equivalence relation on the motion groupoid. And so this allows us to connect the motion groupoid to various different settings. So the first of these is using world lines of motions. So if we take a motion f from n to m prime, then we define the world line of this motion to be ft of n. So we take the union of all the ft of n crossed with t. So we get this path expressing the motion of n inside m cross I. And so it's pretty straightforward to see that if motions have the same world line, then they will be motion equivalent. So we can prove that just by observing that if we look at g to the minus 1 dot f, then just on n, this is really equal to gt to the minus 1 composed with g, because that's exactly the definition of what it means to have the same world line. And then, of course, this is just the identity. And so what that tells us is that g to the minus 1 dot f is n stationary, and therefore g bar star f is path homotopic to a stationary motion. So motions with the same world line give the same motion, are motion equivalent. But what we prove in the paper is a much stronger result, that we can write down the equivalence relation in the motion groupoid completely in terms of what we call level preserving ambient isotopy of their world lines. Their world lines live inside m cross I, so we can construct some isotopy of m cross I fixing the 0 and the 1 boundary and the a cross I that moves the world line of f into the world line of f prime. And this is a significant result because it connects from the motion groupoid picture to the generalized tangle or the defect QFT picture, where equivalence is expressed in terms of isotopy. Okay, and then for the next equivalence relation, I need to set up a bit of new notation. So if we take M to be any manifold and A a subset, there's always a left group action of just, so this is just homeomorphisms from M to M fixing A, and I can act on any subset just by looking at its image.
Sorry, before you go to, it's just a question. Like, given any word line, is it always realized by some motion? Like if I think about the...
So what's an example? So, well, okay, I guess it depends slightly. So, I mean, world line here is something you obtain from emotion.
Yeah.
So it doesn't, I mean, by definition,
Okay.
it only exists. But, so something we do in the paper is to think, so this is where I should have done a Corey style talk, and now I can go off and talk about this instead. But something we do in the paper is to construct what are a natural generalization of the original Artin definition of braids, where we think of these embedded subsets, and then if you construct these topologically, then not every world line or not every embedded subset will extend to, so this is some question about isotopy extension, really, when you have an embedded subset. So the kind of classic example that was on the math side, the motivation for constructing the motion group in the first place, is if you think of a knot in 3 dimensions, then you can gradually move this to the unknot if you don't think about the ambient space
Okay.
in the topological setting.
Yes, but I mean, for a knot, you would, to get an on knot, you have to swap the crossings. When you swap the crossing, there will be a moment when it's not going to be an embedding.
So I don't have to swap the crossings. I just have to gradually shrink all of the knotted
Well, to a point.
to a point.
that's like a cheating.
Right, so this, I mean, but this is exactly the motivation why it's worth doing this, because we want a setup where that we can't cheat.
But like if you restrict in the smooth category, then you
Right,
can shrink.
right, and that's absolutely another option to work in the smooth category. That's another.
Smooth with derivative never zero, actually.
What?
You need smooth map such that the derivative is never zero. Regular. Otherwise, the same monster is going to happen.
Okay.
It's quite tricky.
Okay.
What about a wild unknot? Do you have an unknot?
Tamed.
No.
You only consider tamed and not.
No, but I'm asking if you can get a counterexample this way, right? If you have a wild unknot, you can pull it straight, that makes it an unknot, but that's not smooth. But I guess it's not, maybe you can't realize it by an ambient isotopy. I don't know if you can pull it straight with an ambient isotopy.
If it's not the knot, then you cannot realize it by an ambient isotopy. Yeah, sorry, it's not my seminar. So
Yeah. Okay. I guess the question is what I'm not sure exactly what you were trying to find a counterexample.
He asked if
of.
you had something that looked like a valid world line, is it necessarily? Right?
Okay. Yeah. I see. I mean, yeah, certainly not ambient isotopy, but potentially isotopy. But yeah, and I mean everything we do is in the topological setting, and all of these questions about the smooth setting are open. So.
just a comment. So there's in theory a very strong theorem that if you have a locally flat isotopy of a manifold instead of another manifold, which is compact and it can be covered by an ambient isotopy, which is by Kirby and someone else. However, I've never understood the proof, and the proof black box is things that no one knows, so assuming that this is correct, then it's fine. Sorry. So local flatness is what's needed.
Right. Yeah. Okay. But the point here is you're adding an extra condition to the isotopy that makes this true. Okay. Good. Yeah. Okay. So we always have an action of a homeomorphism on a subset, and this allows us to construct another category very similarly to how we did before, where the morphisms are just triples, now just consisting of a homeomorphism, a subset, and the image under this homeomorphism. And we have very similar notation for this. I try to always use this Gothic script for self-homeomorphisms, so it's clear when we're thinking about flows and when we're thinking about just self-homeomorphisms. And so some interesting things to notice about this category. So we'll also sometimes think, so this homeo M N N prime we said is these triples, but sometimes we'll also identify it and identify it with the projection to the first element. So then when we do that, we can think of equipping these sets with the compact open topology exactly as we did before. And then homeo M empty empty, so with no conditions about subsets, is just exactly my top A M M that I had before. And also homeo M M M is the same. And then each homeo M N N prime is going to be some subset. And in this case, each self-homeomorphism will belong to many such homeo M N N prime. Okay, so now we can define what's called relative path equivalence. So we take two motions f and g from n to n prime, and we say that they're relative path equivalent if we can define a continuous map from I cross I into this space of self-homeomorphisms, such that for all s, looking at just t, the image of t, we get a motion, and it goes from f to g. So I think it's easier to think of this graphically. So as is normal in these kind of path homotopy settings, we're thinking of mapping a square into some space, and our conditions say that the left-hand side of the square must always go to the identity, the right-hand side of the square must be entirely inside n homeo m n n prime, and then the top of the square and the bottom of the square are motions. So in this picture, B and C are going to be equivalent in the motion groupoid, or equivalent up to relative path equivalence, but A and B and C are not equivalent because of this hole in top AHMM, this non-trivial topology that stops us being able to continuously deform A into B. And we prove that these two equivalence relations, this relative path relation and this motion relation, really define precisely the same relation. And so the sort of key ingredients of this proof is essentially direct constructions of the appropriate homotopies, where we use again that these stationary motions give us something normal. And what's really significant about this result about relative path equivalence is that this is precisely the equivalence relation used to define the relative fundamental group. So we can now say that if we fix some subset n and we look at the group of morphisms in the motion groupoid from n to n, this is precisely the relative fundamental group, homeo m empty empty, which again is this, remember, is the same as this top HAMM, and then homeo m n n based at the identity. And this result is what we're going to use later to allow us to construct the functor between the motion groupoid and the mapping class groupoid. Okay, how are we doing for time? We're going by my watch and not that clock, right?
Yeah.
And I started at past. Okay, good. So mapping class groupoids. So again, we take exactly the same things as input. We take a pair with some fixed subset. And then recall that we define this category homeo m n n prime, where our morphisms will be self-homeomorphisms from n to n prime. And then we're going to define our mapping class groupoid just as a quotient of this category. So we say that these self-homeomorphisms f and g from n to n prime are isotopic if we can define a continuous map m cross I to m such that we move only through homeomorphisms from n to n prime and we go from f to g. And this is what we call an isotopy. And it's fairly straightforward to check that these relations really do form a congruence on homeo m. So we can consider the quotient, and then we define the mapping class groupoid to be this quotient where our objects are still the same. We have self-homeomorphisms quotiented by isotopy. Composition now is just composition of self-homeomorphisms, identity homeomorphism, and inverse. Okay, and then we can again use the same result we used before, this tensor homojunction, And this allows us to say that these continuous maps, these isotopies, M cross I to M, really are exactly the same as paths into the space of homeomorphisms. And so what that tells us is that as sets, these morphism sets from n to n prime are really just the pi zero of these spaces of homeomorphisms from n to n prime. And so we can represent that pictorially. So before we had this top HMM, and then we had these paths starting at the identity, and then we had to map these squares in. So now what we have is we just have these points which live inside these darker squares. And notice now maybe in this connected component which doesn't contain the identity. And then our equivalence relation is just a path living completely inside this space of homeomorphisms from n to n prime. Okay, so we can look at some examples. So if we consider our ambient space M to be the unit circle, and we first think of our n as being empty, then we get that the morphisms are equivalent to z over 2z. This can be seen just by noting that the space of homeomorphisms from S1 to itself has two path components, the orientation preserving and the orientation reversing homeomorphisms. And so this means we can just look at the map induced by the degree homeomorphism, and this gives us an isomorphism from the pi 0 to z over 2z.
Is the homotopy to S1 on, say, the orientation preserving component, is that a homotopy of topological groups in any sense? Like, what am I saying here? That what am I saying? I don't know. Does that homotopy somehow, because S1 is a group, a rotation, right? So is this component somehow, the orientation preserving component is homotopic to S1? Is there some way in which that behaves nice with the group structure on S1? It's a big,
I
maybe it's a big question.
suspect the answer is yes.
Okay.
When it's a strong deformation retract.
Oh, if it's a deformation retract?
Yeah.
Okay.
Yeah, okay. Okay, and then we can look at another example. If we look at d squared with the boundary fixed, then we get that this is trivial. So this is a consequence of the Alexander lemma. So if we take any homeomorphism in d squared, we can gradually isotope this away from the boundary. So it's fixing the boundary. We can gradually isotope this away from the boundary to something that is trivial. And moreover, this really does represent a continuous isotopy. Okay, so now we want to ask, when are these two things the same and when are these two things different? So we can construct a functor from the motion groupoid to the mapping class groupoid. So firstly, we define a functor which just takes equivalence classes in the motion groupoid and sends it to the equivalence class of the endpoint in the mapping class groupoid. So this is the identity on objects, and on morphisms we just look at the endpoint of this path. And so to see that this is well defined, we can see this very straightforwardly by just looking at these pictures. So what did it mean for B and C to be equivalent in the motion groupoid? Well, it meant we could map this square in such that the right-hand side of the square was precisely an isotopy in the mapping class groupoid. So that's all we need to check that this is well defined. Okay, and we can straight away prove that if the pi 0 of the space of homeomorphisms from M to M is trivial, this functor is full. And how do we see this? Well, we can see this just by looking at the picture again. So what does it mean for the pi 0 to be trivial? It means that the top HMM has exactly one connected component. So we pick any point in top HMM, and there exists a path from the identity. And this is an if and only if, because if I put any point over here in a different connected component, then I can't construct, by definition, can't construct a path from the identity. To prove when our functor f is faithful, we have to do a bit more work. So to do this, we're going to make use of the long exact sequence of relative fundamental groups. So in general, for any space x and any subspace y, and x0 and y a base point, we have a long exact sequence where we go from the nth fundamental group of y, nth fundamental group of x, to the nth relative fundamental group of x and y, all the way down to 0. Now, what do the maps look like in this long exact sequence? So the I and the J maps are just inclusions. The only one that's a bit more complicated is this partial map, but we're really only going to need the bottom end of this sequence, so I'm just going to say what this is in the D1 case. So the relative fundamental group of x with respect to A is these paths which start at x0 and end in A, up to relative path equivalence. So this equivalence where one endpoint was fixed and one endpoint was allowed to move as long as it stayed within A. And then this map partial just takes a path in here and sends it to something in pi 0 A of x0 by just looking at the endpoint of this path. And we already said that we have precisely that our motion groupoid is this relative fundamental group and our mapping class groupoid is this pi 0. So we can just substitute this into our long exact sequence. So really for now we're only looking at these last few terms. The way we defined our functor f means that if we look at the group case for any n, we just look at the morphisms from n to n, then this partial map is precisely the restriction of f to these groups. So we just have f here and then inclusions everywhere else.
So is f like a generalization of point pushing? Like if you have the Berman exact sequence, is f like the, or is, so this would be a situation where in the braid group, right? Like if you have a braid group and you want to cover up one point, there's an exact sequence relating the braid groups. Well, let's say pure braid groups, right? Or again, if I have a surface with a puncture, and you want to know how does a mapping class group with the surface with the puncture relate when you fill the puncture back in, you get an exact sequence that feels similar to this.
So you're thinking of the puncture as some fixed point.
Yeah.
So you're restricting it's very possible.
There's some pi 1 of the space that comes in.
That's
It's the point pushing. This
sounds
like some generalization.
Sounds like the same thing, but I'd have to double check. But yeah. Okay, so then we can prove the lemma that in the group case, the restriction to these morphism groups is an isomorphism precisely when pi 1 and pi 0 are trivial. Yeah, okay, so the proof of this, I mean, we just look at this exact sequence. If we have this pi 1 is trivial and this pi 0 is trivial, then we get exactly that f is an isomorphism. And then from there, we can prove that this extends to the full category, and we get this theorem that this is a functor precisely when the pi 1 and the 0. This is an isomorphism of categories precisely when the pi 1 and pi 0 are trivial. So what does the proof of this look like? So we already said that it's full, so we just have to check that it's faithful. So we want to look at what happens if we take an f and f prime in the motion groupoid such that their images in the mapping class groupoid are the same. So what does that mean? It means that they're equivalent to the identity, and then we can just use that this is a functor to change this to a star composition in the motion groupoid, and then apply the star composition and use that we can also interchange, or that our inverse is this f prime bar. So we get f prime bar star f, and now we've got a motion from n to n. So then we can use the group case, which says that this can only be true if this f prime bar star f is the same as the identity in the motion groupoid. And what does that mean? It means that if we star compose with the identity, it's path equivalent to a stationary motion, which means that f prime bar star f is path equivalent to a stationary motion. Since we have that the identity star composed with anything is path equivalent to the thing we started with. And so this is precisely the definition of motion equivalence in our category. So we have that these things are motion equivalent, and this is a faithful functor. Okay, so then we can start to look at some examples of what kind of results we can start to say now we've constructed this functor. So in general, for any disk d to the n, if we take d to the n with the boundary fixed, then we always have an isomorphism between the mapping class group and the motion group, or the mapping class groupoid and the motion groupoid. How do we see this? Well, we already used the result. We already gave the example that the mapping class group is always trivial. So pi 0 homeo d squared empty empty is always trivial. And we can actually extend the Alexander trick to any n. So this always works, that the pi 0 is true. And then Hamstrom proved that in general it's also contractible. So that's everything we need to prove that result. I think it's also quite interesting to look at what happens when we don't fix the boundary of d squared. So if we consider the example where we have d squared and we have 2 points in the disk which are equidistant from the center of the disk, then we can consider the path of self-homeomorphisms which gradually rotates the disk by pi. Then we can think of doing this path twice. So we're now gradually rotating our disk. We're rotating our whole disk by 2 pi. So we can kind of intuitively see from this picture, we don't expect that in the motion groupoid we're going to be able to unbraid these strings. But to get a map into the mapping class groupoid, what do? We just look at the endpoint. And what is the endpoint? It's a 2 pi rotation. It's the identity. So the image of this in the mapping class groupoid really is the identity. What other examples can we look at? So we can notice that, in fact, in the case of d squared, the map from the motion groupoid to the mapping class groupoid is neither full nor faithful, because in the mapping class groupoid we have these orientation reversing things as well, which we talked about, and we have in general that pi 1 of the disk is equal to z, where the generating element is precisely this 2 pi rotation. So what we find is an exact sequence that looks like this, where on the left we have this z, these 2 pi rotations, and on the right we have this z over 2z. Okay, and then another example we can look at is if we take m to be S1. So in the case we just looked at, we could kind of get around this non-isomorphism by just fixing the boundary. Whereas in this example we don't have a boundary, so we kind of can't do that trick anymore. So if we take S1 and then we just consider a point in S1, we can do exactly the same 2 pi rotation and get a non-trivial element of the motion groupoid, which becomes something trivial in the mapping class groupoid. And again, we can play exactly the same game by filling in the exact sequence, and we get the same thing, that the pi 1 of the space of homeomorphisms of S1 is Z, the pi 0 is Z over 2Z. But in this case, we also know that if we look one further back in the exact sequence, so we look at pi 1 of homeo S1 PP, so these are paths which send the point P to the point P. This is trivial. So now we get a sequence where we have a zero map between the motion groupoid and the mapping class groupoid. Okay, and I think, yeah, okay, so by my watch it's past half past, so I think probably it makes sense for me to stop there.